We have our next speaker, Leonidas Kosmidis from Barcelona Supercomputing, and you're going to talk about METASAT Demonstrator, some mixed criticality in there, AI, all the good stuff. Thank you.
Thank you. Hi, everyone. I'm Leonidas Kosmidis. I was the coordinator of the METASAT Horizon Europe project. It was a 2-year project that finished in December. And today I'm going to show you the final demo of our project, replicated only using technologies developed in our group. So the idea of this project was that nowadays space processors are really simple, so they cannot really perform high-performance computations. They usually transmit the data in the Earth and then they are processed in Earth. But nowadays we are moving to a new paradigm. We need more powerful hardware in space in order to perform computation there. And we are interested in high-performance computing and also AI. In order to demonstrate this, we created a prototype hardware platform on an FPGA, a VCU 118. And we have modeled a very high-performance space platform that cannot be found nowadays. So we have a multicore, which is based on the space processor NOEL-V from Frontray Geisler. We have integrated our SPARROW SIMD unit. This is a short vector unit that we designed for AI acceleration. And we have integrated also a RISC-V VORTEX GPU in the same SoC. Here we have a qualifiable software stack, which means that we can use the accelerators either from bare metal or from a real-time operating system, and in particular the Artem's SMP operating system, which is qualified for space. We can use OpenMP for parallel computations. We can use TensorFlow Micro and safety-critical graphics APIs. We support mixed criticality, which means that we can have multiple applications with different levels of criticality. We can have very high critical applications that cannot fail, but at the same time they can coexist with a lower criticality software that they can run in best effort manner. And everything is compliant with the RISC-V ISA, and as I will show, we have a quite mature software stack. So now let's move to the demo. Here you can see our FPGA connected to a computer that is used mainly for telemetry and displaying data. And what I'm showing here is 3 different space applications that we have developed. All of them are using AI, and they are running in parallel in the same hardware by sharing the SPARROW unit and the GPU. Here on the top left, we have the high criticality application, which is FDIR, fault detection, isolation, and recovery. Mainly what we do is we read sensor data and we monitor the health of the satellite. So here we display the data. With blue, we have the data of the sensor, and with orange, we have an AI model which looks at the window of the past values and detects anomalies. And when the score goes the anomaly score goes over 2, then we detect an anomaly and we can inform the operator in order to take action. Here on the bottom, we have 2 applications that we have developed in the past for the European Space Agency. They are called OBP Marc ML, onboard data processing machine learning applications. And here on the left, we have a cloud screening application. Mainly it's a segmentation model. We have an input satellite image, and we have to detect whether it's covered by clouds, because in this case, it's a useless image. We don't have to waste bandwidth to transmit it to Earth. And here you can see periodically the output of the segmentation map. It takes a couple of seconds to be accelerated. But what I can tell you is that without our acceleration hardware, this runs 3 times slower. And here on the right, we have another type of application, again applied to satellite images. We have images from sea, and we detect ships in those images. This is much heavier, so it takes much longer to be executed. So you can see that the frequency here it's higher, and these two applications that they have lower criticality execute a bit slower, but still much faster than if they were executed in the scalar processor. And that concludes my demo. Here you have our project's contact and social. Please follow us and pass by our BSc booth if you want to see the demo in more detail and if you want to discuss the details of our hardware.
Thank you so much. Are there any questions? Yeah, sorry. Applause.